Good day, everyone. Welcome to this new entry in the Artemis Summer School Learning Series. I am Aida Himish, a collaborator on a data infrastructure team focused on the AI and digital and data engineering development tasks. And today, we will be talking about the intelligent twin, the digital twin that is enabled and empowered by artificial intelligence to help understand the past and navigate the future of cultural heritage. Let's talk about digital intelligence for cultural heritage. Why should we use AI or this kind of technology in this context? Well, cultural heritage is oftentimes, most times, fragile, either at risk of physical deterioration or at risk of loss in cultural memory, sometimes both, usually both. It is complex. Each cultural heritage element has a rich history that makes it hard to contain into a rigid data structure, just like tabular and standard data structures and databases. It is distributed across different museums and data providers. Different museums have their own collections, data providers that don't want to share it or something of the sort. We want to collect all of this and link them together. And it is also difficult to search and interpret. There's a panoply of results every single time. The results are oftentimes complex, not easily interpretable because of the nuances that the cultural heritage data has, and the fact that people need to understand exactly the differences in order to be able to discern what they need. Today we have huge amounts of digital information, but accessing meaningful insights is still challenging and difficult. When we talk about AI in the context of cultural heritage or advanced technologies in general, we talk about a movement through time. The digital twin system builds on a strong digital foundation or foundations, which would allow users to interact with a query, interact with and query a knowledge graph using natural language. So in this case, we're trying to access that past information, that historical record about all cultural heritage elements. So we're kind of looking through the past during the present, and we're letting AI bridge the possible gaps in the available information, just as we said before, where data is disconnected or dispersed across different databases and different providers. We can also look into the future of cultural heritage by predicting potential deterioration processes. We're trying to protect this heritage by finding out what might happen to it in the future and not only reacting when that is done, but actually anticipating it. So we're trying to predict the damage that would be affecting tangible cultural heritage through predictive models. Another thing that we can look through the future with is simulation of future scenarios. So in this case, we're not trying to find out what's likely to happen, but we're exploring willfully. We're exploring how heritage objects or sites might evolve over time. So we're actually imposing certain conditions and trying to experiment with certain conditions to see what would happen to that physical artifact, object, site, monument, etc. So we're peeking through the past during query and access of that data, but we're also looking into the future with this advanced technology and the fact that we can have all of these processes and these models that allow us to do such tasks. What are the limits of traditional systems? Why are the systems that are here today not enough or still not allowing us these kinds of facilities? Advanced research often requires knowing exactly how the data is structured. So knowing, for example, the ontology background, these are all concepts that have been mentioned in other learning series episodes. So the ontology is how the ontology structures the knowledge graph, how the data is supposed to be searched in detail or as generally as possible, like how high level a query might be in order to get what we need, or how detailed it should be to get exactly what we need. Searching the right keywords. A person looking for an amphora or a person looking for a vase may not get the same results because they need to know if this term is the right one for their query, and so on. Understanding technical query languages. With a lot of knowledge graphs come the need for expertise in querying languages that may not be accessible to everyone, may not be something that everybody knows how to do. Also, navigating through large sets of results. So every query might give about a plethora of results that may not be so easy to read through if you're not an expert in the field, if you don't know exactly what you're looking for again. And so all of this needs to be facilitated somehow. These requirements create a barrier between people and information when a person's trying to ask or query something into the knowledge graph. They need to know all of these things beforehand, and they have to think about the technical aspects more than what they need. So many potential users, students, researchers, or heritage professionals in general may struggle simply because the technology is not designed around natural human questions. So we want to simplify that. We want exactly the opposite of that. So let's ask a simple question instead. What if searching was that easy? Imagine typing, find artworks by artists who studied in Florence during the 16th century. It's a very natural way to communicate with a potential knowledge graph, right? So we're trying to exactly express this sort of intent and let the system understand everything else it needs to understand. We want to make that the job of the system and not of the user. The goal is to make the technology invisible to the user and let them experience it intuitively, where they are able to focus on their research questions, not on the mechanics of the database, how it's organized, what is the ontology, what is all of that stuff. So, what do I want and what am I trying to discover? That is the only thing that the user should be able or should have to worry about during their query. AI can help us do exactly that. How so? The key idea is searching by meaning. We're not trying to search by keyword, by structure. We're trying to search by, again, the intent of the query. Artificial intelligence, in a sense, can transform both our questions, which would be the query, and the data itself in the knowledge graph into numerical representations, as numbers is what works best with a machine, right? So these numerical representations are for the meaning of each element, and they're called vector embeddings. Now, this is a little more technical now, but I want to pick your mind a little bit about how, or something to think about before the summer school is this is a key concept in this entire methodology of how we're searching for this data in a more smart, more efficient and effective way. So these vector embeddings, what are they? The example would be, it's just a list of numbers. These numbers all sort of indicate the representation of that word in a certain context, okay? We're going to see this in a more visual way in the next slide, but you can think of this in general as giving each piece of information a semantic fingerprint, a fingerprint of its own meaning. If two objects then mean something similar, their fingerprints are also going to be close to each other, are also going to be similar. And so that's what we're trying to find when we're searching, is the similar fingerprints. Let's see what these fingerprints can look like. So from numbers to semantics, here we have a little chart of words as vectors. The points are basically a plot of these numbers in a space, and we have two dimensions. We have the age and a gender. You can see here that all of these words are related in some way, contextually. As a human, you can understand that all these words are related. For a machine, it is also the case, and it's not very intuitive to think about it this way, but it is possible with this concept of fingerprints and vector embedding. So grandfather is the older version of a man, and the man is an older version of a boy. They're all aligned according to the gender aspect, but not the age aspect. Same way, woman and girl. But woman is not aligned with a man because they're different genders. These are all things, when you look at this chart this way, you can tell where the similarity can be identified. And this is exactly what the embeddings do, and this is exactly what a machine looks like. Now, these are two dimensions, so it seems a bit simplified, but there's so many dimensions to all of these words, and all of those are encoded in numbers as well. So the similarity of any two words is relative and preserved at different levels of its meaning. And we want to use exactly this method to access, search, and use large knowledge graphs of cultural heritage. What can we achieve and what can we find with the similarity search? We can find fragments belonging to the same object, so pieces of one object that may not have been found by the same people, may not have been cataloged by the same data provider, and still they belong to the same object. So these links, it's a little bit dispersed. These objects that are not maybe explicitly related in the knowledge graph, but we're trying to infer that relationship with this similarity search. Different objects that were excavated at the same site, but from different locations. Again, link that might be missing or not explicit that we are inferring here. Different objects that were crafted in the same workshop. here we are trying to surpass that keyword limitation where a person looking for a bull is not going to get the same results as a person looking for a knife, but they might have the intent of finding the objects that were crafted in the same workshop. And so we were trying to basically allow them to have this sort of link, whether or not they need it, based on their, like, they can discern if they need this information or not. Different objects made of material originating from the same place, and this is inferred from the data of scientific analysis reports, the material composition, specifics about the materials and how the object was made and what it was made of, and these things can pinpoint these similarities. Or different objects made by the same artist. Now, this is also a way to surpass the visual constraint. Sometimes images are not always possible. Sometimes the artifacts are damaged, or you cannot really tell if it's the same artist or not. But you have other information, other metadata around that object that can point to that missing link. Now that we are able to query and look into the past and find out and understand the data that we already have and we already built the knowledge graph of, how about the future of the artifacts? How can we use that data to predict deterioration, for example? To protect cultural heritage, we're trying to anticipate the damage, and with knowledge graphs, we can integrate different types of information: climate data, humidity, temperature, pollution, etc. We can put in material properties, we can put restoration history. How has that artifact or that physical object been taken care of in the past so far? Conditions of the use and display. How has that museum been exposing that artifact, or maybe storing it if it's not been exposed, or using it? By analyzing these factors together, the system identifies patterns of deterioration. It can tell that because of this history of records, this is likely to happen, or if the conditions arrive to this trend, it's going to cause damage, for example. So what do we gain from this? Early warning systems, be able to anticipate damage before it is actually done, to then have better conservation planning, plan how to take care of things before they get lost. More efficient use of resources. You don't have to lose the artifact. You don't have to lose parts of the building. You don't have to lose maybe tools, restoration tools beforehand by doing something that might be useless in the grand scheme of like the restoration process. Evidence-based decision making, and this means that we have a record of facts around that object, and not even just like facts relating to that object specifically, but how it has interacted with everything else around it, with every other cultural heritage element, how it has been used or needed in the past, and what it's been through, to then help us make our decisions in how to preserve it. The next and last point would be simulating the future. So this is a little bit different in the case that, in the sense that we don't want to predict what's likely and what would be like something that would happen realistically. We are trying to explore possible futures, such as, for example, what happens to this monument if the humidity increases by 10%, or if the temperature increases by a number of degrees. We are trying to impose certain conditions that may not be likely, that may not actually happen in real life, but we want to see what would be the result of that. And these simulations are not certain futures, they are just decision support tools that allow us to compare conservation strategies. What if, for example, we want to use this conservation strategy for this artifact, but maybe it's not the best, maybe it's going to lead to potential damage or a hazard? And test restoration plans. If we use these tools for restoration, this, for example, chemical, maybe it's going to backfire on the restoration plan. Evaluate long-term risks that may not be considered from the past and present data. Again, these are not like trends that are predicted from past and present data. This is something that we just want to impose, and we want to explore how that would affect the physical or site or monument, any physical cultural heritage elements that we need to preserve or to take care of. So we want to see what would happen before actually touching the physical object. So we're doing all of this on the digital side. And in this case, the digital twins becomes a safe experimental space to test ideas without touching the actual object. So we have this sort of like undo button that allows us to experiment freely without the risk of losing and damaging the physical element. Now, let's look again at the bigger picture. This is just to kind of recapitulate everything. To fully benefit from AI in cultural heritage, we need first accessible, structured knowledge, and heritage data should be open and interoperable. So we want to find all the data there is, not actually connected in a way that we develop this huge knowledge graph of all this related information that we can learn from and interpret. It needs to be organized as connected knowledge graphs. We want to create all of these links, and we want to make things as coherent as possible within, again, the ontologies and the structure elements that need to be there as a foundation. And it needs to be searchable by anyone, not only technical experts. It needs to be accessible by anyone who needs this data, who wants to find out something without them knowing how to write with SparkQL, which is the language of interrogation, without them knowing what CDOC-CRM is, or ontologies in general, without knowing what a graph is. They just need to be able to ask and receive answers. The same structured data can then power discovery of hidden relationships between objects, so the similarity sort of search that we're implementing and using, predictive models for conservation risks, and also digital twin simulations to explore future scenarios. Now, this is I hope that the presentation has been clear enough and has given enough food for thought. Now, I would like to ask you something before the official lecture at the summer school. How would you search for heritage data today? We know how search engines are. We know how natural language querying is these days. How would you search for something that has to do with cultural heritage today? And what do you want to know about cultural heritage? I want you to think about what aspects of a search is the most important to you. Is it just getting a list of results? Do you look for something else when you're searching? Do you have a whole story that you need to find out, a narrative? Think about these things, and let's take into consideration all the stuff that's been mentioned in this lesson or this video lecture or any other episode before. And see you at the summer school for the rest of the lecture. Thank you very much. And that was all for me.